Section 16.4, the pH scale. The molar concentration of proton in an aqueous solution is usually very small. For convenience, therefore, we usually express the concentration of proton in terms of pH, which is the negative logarithm in base 10 of the concentration of proton. So pH equals the negative log of the concentration of proton. If you need a review of use of logs, see Appendix A. We can use equation 1617 to calculate the pH of a neutral solution at 25 Celsius. That is, one in which the concentration of proton is 1.0 times 10 to the negative 7 molar. The pH is the negative log of 1.0 times 10 to the negative 7 equals negative 7, which is 7. The pH of the neutral solution is 7.00 at 25 degrees Celsius. Notice that the pH is reported with 2 decimal places. We do so because only the numbers to the right of the decimal point are the significant figures in a logarithm. Because our original value for the concentration of 1.0 times 10 to the negative 7 has 2 significant figures, the corresponding pH has 2 decimal places. What happens to the pH of a solution as we make the solution acidic? As acidic solution is one in which the concentration of proton is greater than 1 times 10 to the negative 7 molar. Because of the negative sign in the equation, the pH decreases as the concentration of hydrogen ion increases. For example, the pH of an acidic solution in which the concentration of hydrogen ion is 1.0 times 10 to the negative 3 molar is pH is negative log of 1 times 10 to the negative 3 equals negative times negative 3, which is 3.00. At 25 Celsius, the pH of an acidic solution is less than 7. We can also calculate the pH of a basic solution, one in which the hydroxide concentration is greater than 1 times 10 to the negative 7 molar. Suppose the concentration of hydroxide is 2.0 times 10 to the negative 3 molar. We can use equation 1616 to calculate the concentration of proton for this solution, the equation 1617 to calculate the pH. The concentration of hydrogen ion is the ion constant product divided by the concentration of hydroxide, which is 5 times 10 to the negative 12 molar. And the pH is the negative log of 5 times 10 to the negative 12 molar, which is 11.30. At 25 Celsius, the pH of a basic solution is greater than 7. The relationships among the concentration of proton, hydroxide, and pH are summarized in Table 16.1 and in Figure 16.5. The pH values characteristics of several familiar solutions are also found in Figure 16.5. Notice that a change in the concentration of proton by a factor of 10 causes the pH to change by 1. Thus, the solution of pH 6 has 10 times the concentration of proton as solution with a pH of 7. You might think that when the concentration of proton is very small, as it is for some examples in Figure 16.5, it would be unimportant. Nothing is further from the truth. If the concentration of proton is part of kinetic rate law, then changing its concentration will change its rate. Thus, if the rate law is first order in the concentration of hydrogen ion, doubling its concentration will double the rate even if the change is merely from 1 times 10 to the negative 7 to 2 times 10 to the negative 7. In a biological system, many reactions involve proton transfers and have rates that depend on the concentration of protons. Because of the speeds of these reactions are crucial, the pH of biological fluids must be maintained within narrow limits. For example, human blood has a normal pH of 7.35 to 7.45. Illness and even death can result if the pH varies much from this narrow range. pOH and other P scales. The negative log is also a convenient way of expressing the magnitudes of small quantities. We use the convention that the negative log of a quantity is labeled the P quantity. Thus, we can express the concentration of OH as POH. POH is the negative log of the concentration of hydroxide. Likewise, pKw equals the negative log of the ion concentration constant. By taking the negative log of both sides of equation 1616, the negative log of the concentration of proton plus the negative log of the concentration of hydroxide yields a negative log of the Kw. We obtain the following useful expression. The pH plus the pOH equals 14 at 25 Celsius. We'll see in section 16.8 that p-scales are also useful when working with other equilibrium constants.